Dear students, in this lecture 6 of module 2 Fourier series, I am going to discuss the Fourier series of some functions with arbitrary period 2l which are defined in the intervals of length 2l. In one of the previous lectures, I have discussed that if function with period 2l is defined in the interval of length 2l, that is, if suppose function is defined in the interval minus l to plus l, then its Fourier series is f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n pi x by l plus summation n from 1 to infinity bn sin n pi x by l, where a0 is given by 1 by L integral from minus L to L f of x dx. An is 1 by L integral from minus L to L f of x cos n pi x by L dx. Bn is 1 by L integral from minus L to L f of x sin n pi x by L dx. Now suppose the function f of x which is given to us is even function. Then the value of Bn will be 0, and for an even function the integral from minus L to L will be 2 times integral from 0 to L. So that our formula for a0 will be 2 by L integral from 0 to L f of x dx, and formula for an will be 2 by L integral from 0 to L f of x cos n pi x by L dx. Similarly, if function is odd function, then a0 will be 0, an will be 0, and the formula for bn will be 2 by L integral from 0 to L f of x sin n pi x by L dx. Now, if function f of x is defined in the interval 0 to 2L, then its Fourier series is given by f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n pi x by L plus summation n from 1 to infinity bn sin n pi x by L, where a0 is 1 by L integral from 0 to 2L f of x dx, an is 1 by L integral from 0 to 2L f of x cos n pi x by L dx, and bn is given by 1 by L integral from 0 to 2L f of x sin n pi x by L dx. Now, given function, first we will find whether the function f of x is even or odd. If function is even, then no need to find bn will be 0, and if function is even, the formula for a0 will be 2 by L integral from 0 to L f of x dx, and an will be 2 by L integral from 0 to L f of x cos n pi x by L dx. Similarly, if function is odd, then a0 will be 0, an will be 0, and bn is given by 2 by L integral from 0 to L f of x sin n pi x by L dx. So, for the interval 0 to L, function f of x is even if it satisfies the condition f of 2l minus x equal to f of x, and function is odd if f of 2l minus x equal to minus f of x. If function is even, then Fourier series will contain only cosine terms, and if function is odd, then Fourier series will contain only sine terms. Now look at this problem. We need to find Fourier series expansion of the function f of x equal to e power minus x, and f of x is defined over the interval minus L to plus L. So, before finding Fourier series, we will find whether the function is even or odd. Since the interval is minus L to plus L, function is even if f of minus x equal to f of x, and function is odd if f of minus x equal to minus f of x. So, f of minus x is Replacing x by minus x on both sides of f of x equal to e power minus x, we get f of minus x equal to e power x, which is not equal to f of x. Also, f of minus x is not equal to minus f of x. So, function is neither even nor odd. So, our Fourier series expansion of f of x equal to e power minus x will be f of x equal to a naught by 2 plus summation n from 1 to infinity a n cos n pi x by l plus summation n from 1 to infinity bn sin n pi x by l. Since function is neither even nor odd, we need to find a naught, an, bn, all these Fourier coefficients. First, let us find a naught. What is the formula for a naught? A naught is 1 by L integral from minus L to L f of x dx. Substitute for f of x, we will get a naught equal to 1 by L integral from minus L to L e power minus x dx. Then integral of e power minus x is e power minus x divided by minus 1. Apply the limits x from minus L to plus L. We get 1 by minus L into e power minus L minus e power plus L, or e power L minus e power minus L divided by L. Now we have the definition of sine hyperbolic function sin hx equal to e power x minus e power minus x by 2, or e power x minus e power minus x is 2 sin hx. Now replacing x by L, we can write the numerator e power L minus e power minus L is 2 sin hyperbolic L. So our a naught becomes a naught is equal to 2 sin hl divided by L. Next we will find an. Formula for an is 1 by L integral from minus L to L f of x cos n pi x by L dx. Substitute for f of x. An is 1 by L integral from minus L to L e power minus x cos n pi x by L dx. Now we integrate this using the standard result or standard integral formula. Integral e power ax cos bx dx equal to e power ax divided by a square plus b square into a cos bx plus b sin bx. We take a equal to minus 1 and b equal to n pi by L. So an will be equal to 1 by L into, by applying this result, e power minus x divided by minus 1 the square plus n pi by L whole square into minus cos n pi x by L plus n pi by L sin n pi x by L. Apply the limits from minus L to plus L. Now here, if we apply the limit, upper limit x equal to L, we get within the square bracket here minus cos n pi L by L, that is minus cos n pi, and we know that cos n pi is minus 1 raised to L, and sin n pi x by L, taking x equal to L, we get sin n pi, and the standard result sin n pi equal to 0 we have. So using this and applying the lower limit, we get an equal to 1 by L into L square by L square plus n square pi square into minus e power minus L minus 1 raised to n plus e power L into minus 1 raised to n. So here minus 1 raised to n is common in these two terms. Take outside the bracket. Simplifying, we get an equal to minus 1 raised to n into L into e power L minus e power minus L divided by L square plus n square pi square, and e power L minus e power minus L is 2 sin hl. So we get an equal to 2L sin hl minus 1 raised to n divided by L square plus n square pi square. Next we will find Bn. Bn is 1 by L integral from minus L to L f of x sin n by x by L dx. Substitute for f of x and then integrate using standard integral formula. Integral e power ax sin bx dx equal to e power ax divided by a square plus b square a sin bx minus b cos bx. Take a equal to minus 1 and b equal to n pi by L. So in the next step we get 1 by L into e power minus x divided by minus 1 the whole square plus n pi by L the whole square into minus sin n pi x by L minus n pi by L cos n pi x by L. Then apply the limits from minus L to plus L. Here also make use of the results. Cos n pi equal to minus 1 raised to n and sin n pi equal to 0. So we get Bn equal to 1 by L into L square divided by L square plus n square pi square n pi by L into minus e power minus L minus 1 raised to n plus e power L into minus 1 raised to n, or Bn equal to 2n pi sin hl into minus 1 raised to n divided by L square plus n square pi square. Next we substitute the values of a0 and a0, an, bn in the series. We get f of x equal to sin hl divided by L plus summation n from 1 to infinity 2L sin hl minus 1 raised to n divided by L square plus n square pi square into cos n pi x by L plus summation n from 1 to infinity 2n pi sin hl into minus 1 raised to n divided by L square plus n square pi square sin n pi x by L. So this is our required Fourier series expansion of function f of x equal to e power minus x in the interval minus L to plus L. Next question. Find the Fourier series expansion of function f of x, and here note that f of x is defined as 1 plus 4x by 3 in the interval minus 3 by 2 to 0, and f of x is 1 minus 4x by 3 in the interval 0 to 3 by 2. So also deduce that pi square by 8 equal to 1 plus 1 by 3 square plus 1 by 5 square plus etc. So now concentrate on the first part of the question. We will find the Fourier series expansion and then we get the series second part given in the second part of the question from the Fourier series expansion. So before finding the Fourier series expansion of given function f of x, we find whether the function given is even or odd. So here function is defined in the interval minus 3 by 2 to 0 and 0 to 3 by 2. So it is defined from, the function is defined from minus 3 by 2 to plus 3 by 2. That is, it is of the form, the interval is of the form minus L to plus L. So comparing, we get L equal to 3 by 2. Next we will find whether the function is even or odd. For the interval minus L to L, we check whether f of minus x equal to f of x or minus f of x. So what is f of minus x? F of minus x is, replace x by minus x in the first function. So 1 plus 4 into minus x by 3, or 1 minus 4x by 3, which is nothing but f of x only. So the function is even function. So we can write Bn equal to 0. So what is the Fourier series expansion? It is nothing but f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n pi x by L. Then substitute for L. We have L equal to 3 by 2. So it becomes f of x equal to a0 by 2 plus summation an cos n pi x by 3 by 2. Or we can write summation n from 1 to infinity an cos 2n pi x by 3. Then we will find a0 and an. Substitute back in this Fourier series. So what is a0 formula? Formula for a0 for even function, it is 2 by L integral from 0 to L f of x dx. And substitute for L. So 2 by 3 by 2, or we can write 4 by 3 into integral from 0 to 3 by 2. In the interval 0 to 3 by 2, the given function is defined as 1 minus 4x by 3. So we substitute f of x is 1 minus 4x by 3. Then integrate 4 by 3 into integral of 1 is x. Integral of 4x by 3 is 4x square by 6. So then apply the limits x from 0 to 3 by 2. Simplify, we will get a0 equal to 0. Then we will find an. Formula for an is 2 by L integral from 0 to L f of x cos n by x by L dx. Now substitute for L and f of x. L we have 3 by 2, so it becomes 2 by 3 by 2 or 4 by 3 into integral from 0 to 3 by 2, and in the interval 0 to 3 by 2 we have f of x is 1 minus 4x by 3. So we'll get integral 0 to 3 by 2 1 minus 4x by 3 cos 2 n by x by 3 dx. So we integrate this using Bernoulli's rule of integration by parts, that is integral uv dx equal to u v1 minus u dash v2 plus u double dash v3 minus etc. Here u dash derivative of u double dash is derivative of u dash etc. And v1 is integral of v, v2 is integral of v1 etc. So we take u equal to 1 minus 4x by 3 and v equal to cos 2n by x by 3. So the first term is, here we have 4 by 3 into first term u v1. U is 1 minus 4x by 3. v1 integral of v, that is integral of cos 2n by x by 3. Integral of cos 2n by x by 3 is sin 2n by x by 3 whole divided by 2n by 3, or 3 by 2n pi into sin 2n pi x by 3. Next minus u dash v2. U dash derivative of u, derivative of 1 minus 4x by 3. It is 0 minus 4 by 3 or minus 4 by 3 into v2. v2 is integral of v1. v1 is this 3 by 2n pi sin 2n pi x by 3. Its integral is, see 3 by 2n pi is constant, keep as it is. Integral of sin 2n pi x by 3 is minus cos 2n pi x by 3 whole divided by 2n pi by 3, or we can write minus 9 by 4 n square pi square cos 2n pi x by 3. Then apply the limits 0 to 3 by 2. So simplifying, we get an equal to 4 into 1 minus 1 raised to n divided by n square pi square. Next we substitute the values of a0 and an in the series. We get f of x equal to summation n from 1 to infinity 4 into 1 minus 1 raised to n divided by n square pi square cos 2 n pi x by 3. Then to get the series in the given in the second part of the question, we take x equal to 0 on both sides of this Fourier series. So we get f of 0 equal to summation n from 1 to infinity 4 into 1 minus 1 raised to n by n square pi square into cos 0. Cos 0 is 1. So what is f of 0? F of x is 1 plus 4x by 3. Given function, we have f of x is defined as 1 plus 4x by 3 at x equal to 0. So f of 0 is 1, and right hand side expanding the summation, taking n equal to 1, 2, 3 etc. we get 1 equal to 8 by pi square into 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus etc. Or we can write pi square by 8 equal to 1 plus 1 by 3 square plus 1 by 5 square plus etc. So this is the required series given in the second part of the question. So our next problem is obtain the Fourier expansion of f of x equal to pi x in the interval 0 to 1, pi into 2 minus x in the interval 1 to 2. Reduce that pi square by 8 equals to 1 plus 1 by 3 square plus 1 by 5 square plus etc. So here first let us find whether the function is even or odd, and before that find the value of L here. So function is defined in the interval 0 to 1, then 1 to 2. So it is defined in the interval 0 to 2. So the function is defined in an interval of the form 0, 2L. So comparing interval 0, 2 with interval 0, 2L, we get 2L equal to 2 or L equal to 1. Then we find whether the function is odd or even. So here for the interval 0 to 2L, the function is even if f of 2L minus x equal to f of x, and function is odd if f of 2L minus x equal to minus f of x. Now what is f of 2L minus x? F of 2L minus x is, since the 2L is 2, we get f of 2 minus x, and f of 2 minus x, replace x by 2 minus x in the function f of x. So f of 2 minus x equal to pi into 2 minus x, which is nothing but f of x. So we have function is even function, hence we can write Pn equal to 0. If function is even function, the Fourier series will contain only cosine term, and it is given by f of x equal to a0 by 2 plus summation an cos n by x by L. Now here, since L equal to 1, this becomes f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n by x. Next we will find a0. Formula for a0 is 2 by L integral from 0 to L f of x dx. Substitute for L. L is 1. So 2 by 1 integral from 0 to 1, and in the interval 0 to 1, the function is defined as pi into x. So substitute and then integrate pi into integral of x is x square by 2. Put the limits x from 0 to 1. We get a0 equal to pi. Then an is 2 by L integral from 0 to L f of x cos n by x by L dx. Put L equal to 1. We get 2 by 1 integral from 0 to 1 pi x into cos n by x dx. Next, pi is constant. We can take outside the integral, and we can you can integrate this taking x equal to u and cos n by x equal to v, and using Bernoulli's rule of integration by parts, integral uv dx equal to u v1 minus u dash v2 plus u double dash v3, etc. So here 2 pi into, in bracket, u into v1, that is x into v1 integral of v cos n by x integral sin n by x divided by n pi minus u dash. U dash is derivative of u, that is derivative of x, 1 it is. Then v2 integral of v1 integral of sin n by x by n pi is minus cos n by x by n square pi square. Then apply the limits integral from 0 to, apply the limits x from 0 to 1. We get an equal to 2 by pi n square minus 1 power n minus 1. Substitute the values of a0 and an in the series. We get the required Fourier series as f of x equal to pi by 2 plus summation n from 1 to infinity 2 by pi n square into minus 1 raised to n minus 1 cos n pi x. Next, to get the series given in the second part of the question, we take x equal to 0 on both sides of this Fourier series. So we get in the next step f of 0 equal to pi by 2 plus summation n from 1 to infinity 2 by pi n square minus 1 raised to n minus 1 into cos 0. Cos 0 is 1. So we'll get this right hand side pi by 2 plus summation n from 1 to infinity 2 by pi n square minus 1 raised to n minus 1. Now by the definition of function, given function f of x, we have f of 0 is 0. So in the next step, we rearrange, okay, and write. So we'll get pi square by 8 equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus etc., which is the required series that is given in the second part of the question. Next question. Find the Fourier series expansion of f of x equal to 2x minus x square in the interval 0, 3, and hence deduce that 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square plus etc. equals to pi square by 12. So here first we'll find whether the function is even or odd. So for that, first we'll find the value of L. Now the given function is defined in the interval 0, 3. So this interval is of the form 0, 2L. So comparing 0, 3, interval 0, 3 with interval 0, 2L, we will get 2L equal to 3, or we can write L equal to 3 by 2. Next, if f of 2L minus x equal to f of x, then function is even, and if f of 2L minus x equal to minus f of x, then function is odd. So these are the conditions for function to be even or odd in the interval 0, 2L, and we can easily verify that this function is neither even nor odd. So the Fourier series expansion is given by f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n pi x by L plus summation n from 1 to infinity dn sin n pi x by L. So in the next step, we substitute for L and we write the series as f of x equal to a0 by 2 plus summation an cos 2 n pi x by 3. Substituting for L, so we have n pi x by 3 by 2, or we can write 2 n pi x by 3. Similarly, next term summation bn sin 2 n pi x by 3. Next we will find a0. Formula for a0 is 1 by L integral from 0 to 2L f of x dx. Substitute for L and f of x, and integral of x is x square by 2, integral of x square is x cube by 3, and we apply the limits x from 0 to 3, and simplifying we get a0 equal to 0. Next we will find an. Formula for an is equal to 1 by L integral from 0 to 2L f of x cos n pi x by L dx. Substitute for L and f of x. 1 by 3 by 2, or we can write 2 by 3 into integral from 0 to 3 2x minus x square cos 2 n pi x by 3 dx. Then we use integration by parts rule. We take u equal to 2x minus x square and v equal to cos 2 n pi x by 3 and integrate this. So first term 2 by 3 into, we have u v1, so 2x minus x square into integral of v, integral of cos 2 n pi x by 3 is sin 2 n pi x by 3 whole divided by 2 n pi by 3, or we can write 2x minus x square into 3 by 2 n pi into sin 2 n pi x by 3 minus u dash v2. U dash is derivative of 2x minus x square, that is 2 minus 2x, and v2. v2 is integral of v1. We have v1 is 3 by 2 n pi sin 2 n pi x by 3. Its integral is 3 by 2 n pi into minus cos 2 n pi x by 3 divided by 2 n pi by 3, or we can write multiplying minus 9 by 4 n square pi square cos 2 n pi x by 3. Next plus u double dash v3. U double dash is derivative of 2 minus 2x, that is 0 minus 2 minus 2. So we have v3 integral of v2 minus 27 by 8 n cube pi cube sin 2 n pi x by 3. So we stop here, we apply the limits x from 0 to 3. If you apply the limits for the terms containing sine function, upper limit x equal to 3, we get sine 2n pi 3 by 3, 3 cancels, sine 2n pi, we get 0. Similarly at the lower limit, sine 0, 0. So the first and last terms inside the square bracket become 0. Apply the limit for the middle. Put x equal to 3. So we'll get cos 2n pi, and we know that cos 2n pi is 1. So at the upper limit, the middle term becomes minus 2 minus 6 into minus 9 by 4n square pi square, that is minus 36 by 4n square pi square. And at the lower limit, if you take x equal to 0, we have cos 0 is 1, and here we have 2 minus 0 into minus 9 by 4n square pi square, that is you will get the minus 18 by 4n square pi square. And simplifying, we get an equal to minus 9n square pi square. Similarly, we will find the value of bn. Bn formula is 1 by L integral from 0 to 2L f of x sin n pi x by L dx, and then we substitute for L and f of x. So 2 by 3 integral from 0 to 3 2x minus x square sin 2 n pi x by 3 dx. We integrate this by taking u equal to 2x minus x square and v equal to sin 2 n pi x by 3. We get Bn equal to (3 by n pi). Next, we substitute the values of a0, an, bn in the series. We get the required Fourier series f of x equal to summation n from 1 to infinity minus 9 by n square pi square cos 2 n pi x by 3 plus summation n from 1 to infinity 3 by n pi sin 2 n pi x by 3. Now to deduce the series given in the second part of the question, we need to take x equal to 3 by 2. So we take x equal to 3 by 2. Left side will be f of 3 by 2. Right hand side, first term, here we have in the summation, if you take x equal to 3 by 2, you will get cos n pi. And second term, second summation, if we take x equal to 3 by 2, it becomes sin n pi. And we know that sin n pi is 0. So the entire second term becomes 0. So we have f of 3 by 2 equal to summation n from 1 to infinity minus 9 by n square pi square cos n pi. Then by the definition of f of x, we have f of 3 by 2 is 3 minus 9 by 4. The definition of f of x is 2x minus x square. If you take x equal to 3 by 2, we get the 2 into 3 by 2 minus 3 by 2 the whole square, that is 3 minus 9 by 4. Right hand side, we have cos n pi is minus 1 raised to n. Then left side, simplify this. Left side will be 12 minus 9 by 4, that is 3 by 4. And right side, we can take 9 by pi square outside the summation, and then we expand the summation in the right hand side. We take n equal to 1, 2, 3. So in the next step, we will get 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square plus etc. equal to pi square by 12, which is the required series, the series given in the second part of the question. This completes the solutions of all the problems in this lecture. Thank you.